this class we are going to see a new downstream process or a new unit operation, that is crystallization. So in crystallization what do? We try to recover the product in a solid form, in a very pure form. So crystallization generally yields a very pure product. Generally crystallization is done at the very end of the downstream process. So that means you have performed several steps like recovery, purification of the product, and then you want to make the product in a solid form. So this is generally in the end of your downstream. Crystallization can also help you to remove impurities. That means only your product will crystallize from the mother liquor, whereas the impurities are left behind. Impurities could be small molecules or even proteins and so on. You can also do crystallization to remove solvent or water, because you are making solid from a solution, so obviously you are removing the liquid, the water or the solvent. Sometimes the consumer would like to formulate the product in a solid form. So the consumer might be expecting the product to be handed over to him in a solid form, or we can even achieve product stability by converting your product into a solid form, because as you know, if you have water present in your product, it may lead to contamination, microbial growth. Sometimes water might not be very good for certain biomolecules, so you want to completely dry your product so there is no contamination, so you can have a long term stability or shelf life of your product. So because of all these reasons, we resort to crystallization of your product. So it is a purification technique and we can achieve very pure solid product, that is the advantage of crystallization. So there is a difference between precipitation and crystallization. So if a reaction takes place, you are going to get a solid out of it, that is called precipitation. There we are not bothered about the form in which the solid is. You are not bothered whether it is a crystal or whether it is amorphous or a combination of everything, but there you get a product, so that is called precipitate. Whereas in crystallization you resort to crystallization in order to get product solid in certain shape and size or in a form of a crystal. A crystal has a defined shape and size, and we are going to look at different types of crystals as we go along in this particular course. So crystal has a shape and size, so crystallization leads to the product in a particular shape and size, whereas in a precipitation you are not bothered about the form of the solid. It could be amorphous, it could be like a gel, it could be crystallized, it could be a combination of all these things. So that is the difference between a crystallization as vis-a-vis the precipitation. So what is the principle or objective of crystallization? So it is a natural or artificial process. That means in an artificial process we induce crystallization by adding some chemical or heating and so on. Actually the idea is to form solid crystals from a solution. The solution is generally called a supersaturated solution. In normal solution we will not get crystals, but we need to make it into a supersaturated. So we can make crystals out of pharmaceuticals. So many drugs have crystalline form, fine chemicals are formed in the crystals, agrochemicals for example, look at some of the pesticides, they are in the form of crystals. Some of the food and cosmetic products, they are in the form of crystals. So you get very pure product which can be then taken for further formulation. So many pharmaceutical, fine chemicals, agrochemicals, food products, cosmetics, they are all in the form of crystals. So generally crystallization is almost the last purification stage in your downstream processing actually. So we might have all done this type of experiment long time back when we are kids. So how do you get sugar crystals? We take impure sugar, put it in water, keep on adding lot of sugar into it so that the solution becomes saturated. Now when we start little bit heating, what happens, whatever solid sugar that is not precipitated, that is in the precipitated form, that has not dissolved also will get dissolved actually. So when we bring up the temperature, all the sugar will get completely dissolved, only impurities may be left behind. Okay, now we can filter and remove the impurities if you want, or we can use a decantation so that the top saturated sugar solution is taken, and now when we reduce the temperature, what happens, whatever sugar that is dissolved, because as you keep reducing the temperature, the solubility of the sugar in water goes down, so the solution becomes super saturated and you start getting nice beautiful crystals of sugar. Remember, you must have done this. So this is one way of separating sugar from impurities. So the impurities are not soluble, so sugar is soluble, so you add all the sugar, impure solid, raise the temperature so that the sugar completely dissolves, whatever solids that are left behind is precipitated, which you filter it out, then you bring down the temperature, sugar comes out as beautiful crystals, and this sugar will be very pure because you have removed all the impurities. So this is one good way of separating sugar from its impurities, so the solid impurities. Same thing you can do for salt. In fact, sodium chloride, you get beautiful white crystals of sodium chloride by doing this particular operation. So fine chemicals are done the same way to get pure solid fine chemicals. So it is a solid liquid separation process. So what you are doing, you are removing the solid from a solution containing the dissolved solid. Okay. So there is a mass transfer of a solute occurs from the liquid to the solid phase. So the solid that is present inside the solution starts coming out. It yields uniform sized and shaped crystals, because crystals, as you know, has a certain size and shape. So as you do crystallization, you are continuously getting the uniform sized solid out of the solution, and then later on you can go resort to centrifugation or filtration to remove the solid from the liquid, and then we can go to drying. So a crystalline product will always have a better appearance than a precipitated product, so the consumer is very happy and they accept your product. That is the reason why you resort to crystallization. So how do you initiate crystallization? So you can initiate crystallization by heating so that the water or solvent starts evaporating, so that the solution becomes more concentrated and reaches a supersaturation, or we can reduce the temperature, that is cooling. So as you keep cooling, again the solubility goes down in temperature, again the solution becomes supersaturated. So the key here is getting a supersaturated solution. When you have a supersaturated solution, it is thermodynamically unstable, the solid will automatically start coming out in a crystallized form. Okay. So what is saturation? Saturation is the maximum concentration of the solute which is thermodynamically stable in that solution. So supersaturation is the solution which contains more of solute than what should be present in saturated. So supersaturated solutions are thermodynamically unstable, and even small disturbances, even impurities present can make the solids to come out as crystals. So supersaturated solutions are extremely unstable, and sometimes you can add some seed crystals so that the crystallization process is initiated. Sometimes the surface of the vessel, if it is rough, sometimes the crystals are formed, or if there are impurities present, then again crystals are formed. So it is highly unstable system. So the degree of supersaturation can be measured in terms of a number which is called the supersaturation coefficient. Okay. So S is equal to Ct, that is the concentration of the solute in a solvent at a given temperature, divided by concentration of the solute in solvent in a saturated solution at the same temperature. So C naught is the concentration at saturated, and C T is the concentration currently that is present in the solution. So if S is equal to 1, that means your solution is saturated. If S is greater than 1, then the solution is supersaturated. Okay. Whereas if S is less than 1, then we can say it is undersaturated. That means we can still add some more solute, and that solute will dissolve freely and nicely in the solvent. So the crystallization theory states that there is going to be a nucleation and then the crystal growth. That means first you should have a nucleation. So if you have a solution containing your solute in a supersaturated state, you need nucleus initially, and then that nucleus will start growing. That phase of those nuclei or the crystals will start growing, and that is how the crystals grow. So when you do not have any solid particles, you need to have nucleation, whereas if you are adding a seed particle, then crystals will grow around that seed. So the driving force for both these steps is the supersaturation. So that is the driving force which pushes the solute which is in the solution phase into the solid phase. So the supersaturated state contains 3 zones. One is called the metastable zone, intermediate zone, a labile zone. So 3 zones which determines the supersaturated states, and let us look at each one of them little bit in detail. A labile zone. So what is a labile zone? Labile zone, the nuclei are formed spontaneously from a clear solution. So if I have a solution, immediately it forms nuclei. Intermediate zone is formation of new nuclei and the crystals as well. That means the crystals also grow, nuclei are also formed. So that is called the intermediate zone. Metastable zone, the crystals, existing crystals start growing. That means no new crystals are formed or no new nuclei are formed. Okay. So in the metastable zone, whatever crystals are present will start growing. In the labile zone, new nuclei are formed, whereas in the intermediate zone, not only new nuclei are formed, but also the crystals also grow. So these are the 3 zones in which the supersaturation crystallization process could be grouped into. So if you have labile or intermediate zone, you will be forming new crystals or new nuclei all the time, whereas in the metastable zone you are not forming new crystals, but the existing crystals start growing, that they become bigger and bigger and bigger, and so on actually. So let us look at what is a crystal. A crystal contains infinite number of unit cells. So there are something called unit cell, okay, a 3-dimensional cell, and crystal will have a repetition of this unit cell in all directions, x, y, z direction. Okay. So unit cell is the smallest unit of a crystal. So if you take a crystal and keep breaking smaller, it will come to a single 3-dimensional structure, okay, which is a repetition of many times, which makes the crystal. So the whole crystal is made up of these small unit cells. Okay. So the crystal has totally 6 numbers, okay, 3 lengths A, B, C, and 3 angles, interaxial angles, alpha, beta, gamma. So any crystal could be described with these 6 numbers, the 3 lengths A, B, C, alpha, beta, gamma. So you can have different combinations of this, so you get different types of crystals. Sometimes you can have A equal to B equal to C, so you will get something like a cube. Sometimes you will have A and B may be equal, C is not equal, sometimes none of them are equal. Same thing with the angles, sometimes the angles are 90 degrees, sometimes the angles are not 90 degrees, the angles are much less than 90 degrees. So you have a large number of permutation combinations, but still they can grouped into beautiful structures or unit cells. So these are the 7 crystal classes. Okay, there are 7 crystal classes. One is called the cubic, next one is called the tetragonal, next one is called the orthorhombic, another one is called the hexagonal, another one is called the monoclinic, you have the trigonal and triclinic. So you see each one of them, the ABCs are different, alpha, beta, gamma are different. Cubic is the most simple, very nice regular system where A, B, C are equal, alpha, beta, gamma are equal to 90 degrees. Okay, we all know this. But then you can have situations where A equal to B, but they are not equal to C. Then that is called tetragonal. Again, the angles are 90 degrees. Okay. Now look at orthorhombic, where A is not equal to B, B is not equal to C, but alpha, beta, gamma are 90 degrees. Then comes the hexagonal where gamma is 120 but alpha and beta are 90 degrees, A equal to B, B is not equal to C. Then in trigonal A equal to B equal to C but gamma is not 90 degrees. Then we have monoclinic where A is not equal to B, not equal to C, alpha and gamma are 90 but beta is 120. Then we have triclinic where nothing is equal, A is not equal to B, B is not equal to C, alpha is not equal to beta, beta is not equal to gamma and gamma is not equal to 90 degrees. So this is the most different system, whereas this is the most symmetric system. So this is the most unsymmetric, different, this is the most symmetric and similar system, that is called the cubic. Now these are the 7 crystal classes. Now there are some more variations in these crystal classes, right. We can have the body centered or the face centered. What is a body centered? You have an atom present inside the 3-dimensional structure, that is called the body centered, like that is the eye. Face centered means you have an atom present on the face of the crystal, okay. So in the cubic we can have a cube with atoms present only in the corners. We can have a situation where atoms present in the corners as well as in the center, okay, that is called body centered eye. Or we can have atoms present in the corners as well as atoms present on the face, that is called the face centered. So in a cubic we can have all 3 situations, whereas in a tetragonal you can have the basic structure, that is corner, but you can also have with the body centered as well. If you look at orthorhombic, we can have corners, we can have body centered, we can have face centered, and we can also have side centered, okay, that means only the side has, nothing else. In a hexagonal we cannot have anything in the body, right, because it is slightly unsymmetric. Same thing with trigonal, same, whereas in monoclinic we can have not only the basic structure but also in the side centered. In a triclinic we cannot have body or face centered, we can have only the basic structure. So if we add all these then we get 14, right, that is called 14 Bravais lattices. So a crystal, there are 7 crystal classes and there are 14 Bravais lattices. So any solid when it crystallizes out will fall into one of these. So beautiful that we can easily put them into. The advantage is once you put them into that class, properties of many of these classes have been well documented. So we can tell maybe some idea about its melting point, some idea about its dimensions, purities, other properties can be sort of guessed based on which class it falls into. So all crystals will fall under 7 crystal classes, that is these: cubic, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic, triclinic, or it will fall under 14 Bravais lattices. Okay, that is to do with the physics of it. Now let us go back again to the engineering side of it. So crystallization occurs only in a supersaturated solution. You need to have a primary nucleation, that is homogeneous nucleation due to flocculation on a molecular level, or we can induce by adding very fine particles, that means we can add to initiate crystallization. But when it is happening because of nucleation, then your product will be of non-uniform size crystals, whereas when you add certain crystals of known size, of uniform size, then the product will also be uniform size. So generally we like to prefer this. So what do? We make a supersaturated solution and quickly add crystals of exact size, then the product also will be of uniform size of one particular size, no, it is a monodispersed one size. Whereas if you allow it to nucleate and then crystallize, you may have a polydispersed system rather than a monodispersed system. And generally solubility of small crystals is greater than that of the large crystals. So when supersaturation has happened, crystallization is happening, the solid present or the solute present in the solution starts coming out as crystals. So what happens? Supersaturated solution starts becoming saturated, and it is going to become less saturated. At that point of time, some crystals can dissolve and again go into solution, right. So there can be a sort of a dynamic equilibrium. In that situation, small crystals can go into solution, large crystals will take much longer time to dissolve. So in supersaturated solutions, the small crystals will dissolve and large crystals will grow. The rate of growth of a crystal depends upon the transport of material to the surface of the crystal, because the solute is present in the bulk solution, it has to get transported and come to the crystal surface, and then surface deposition. How does this solid gets deposited on the surface of the crystal? Okay, so there could be repulsive forces, there could be attractive forces and so on. So the mechanism of that deposition process. So these two things affect the rate of growth of crystal actually. So we can do stirring so that the material gets transported and come to the surface. The rate of growth of crystal is a diffusion control process actually. Okay, so it is diffusion control process, and if there are impurities present, the rate of crystal growth also comes down. So the crystallization process becomes slowed down because of presence of impurity. So the whole process is diffusion control. Ideally I would like to do the crystallization very fast, I would like to have uniform sized crystals. This is an ideal situation, but what happens, the crystallization may be fast for some time, and after some time it will be very slow, number 1. Number 2, although we would like to have a mono dispersed system, how do you achieve mono dispersed system? I said we can seed it with some known sized uniform particle, but sometimes nucleation also happens, and then you may end up with the polydispersed system or polydispersed product. So the rate of growth of a crystal phase is defined as the distance moved per unit time in a direction perpendicular to the phase. As I said, we have crystals either monoclinic or orthorhombic or cubic, so it will slowly getting bigger and bigger, so the phase of the crystal starts moving with time. That is what we call the growth of the crystal. So growth of the crystal takes place only at the outer surface, layer by layer, so it does not happen inside. So outer surface keeps becoming bigger and bigger in a direction perpendicular to that. So the solute molecules will diffuse through the solution and then reach the phases, and then it gets integrated with the phase of the solid crystal surface. So this diffusion process can be defined like this: dm by dt is equal to Ka C minus C star. Okay, m is the crystal mass. So dm by dt is the rate at which the crystal mass is growing. This is equal to K. K is some transfer coefficient, some mass transfer coefficient or crystal growth coefficient. A is the surface area of the crystal growth. Okay, C minus C star is the driving force. C is the concentration of the supersaturated solution, and C star is the concentration of the saturated solution. Once the solution becomes saturated, you are not going to have solute spontaneously coming out as a solid, right. So this is the driving force, C minus C star. A is the surface area of the crystal, m is the crystal mass. So this K is both mass transfer coefficient, that means mass transfer of the solute from the bulk coming down to near the crystal surface, as well as the surface reaction when this new solid gets attached or get embedded with the crystal surface. Okay. So we cannot solve this equation because crystal mass is also going up with time, area is also growing up with time. Okay. So it is not so easy. So the crystallization process has been slightly simplified. It is called the McCabe process, where we say all crystals that are geometrically similar and of the same material in the same solution grow at the same rate. Okay. Then growth is a function of the increase in length delta L. Okay. So we can just look at the linear dimension, in which it is growing, and that we call it as the rate of growth of the crystal. If you are doing at the same material, same solution and the same operating condition. So it is independent of the initial size of the crystal. So if whether the crystal is in micron size or whether it has grown bigger, so the delta L talks about that is delta L is the increase in the length, talks about the growth. So we can say the overall crystal growth is delta L by dt. Delta L is the increase in length, delta t is the time, and we say delta L by delta t is constant. Okay. So irrespective of the size of the crystal, whether the crystal is very small or after about few hours it has become bigger, delta L by delta t, that is the growth rate which is constant. This is one of the rules. Okay. So this is applicable for crystal growth of many materials, but it has to be smaller, around up to 0.3 mm. But it is not applicable when we have very large crystals or when we resort to different treatment strategies during the crystallization. As you know, in crystallization process, what do? Sometimes we heat, sometimes we cool, sometimes we stir, we do so many different processes so that the crystallization happens. So then it is not valid, but until then we can say the rate of transfer and the way the crystals grow, that is the growth rate, is equal to delta L by delta t, that is mm by hour, and it is constant. There are many types of crystallizers available in the market. Some are called forced circulation crystallizer, Oslo type crystallizer, draft tube baffle crystallizer, induced circulation crystallizer, and so on. So each one has different types of designs, and each one are used for certain applications, and each one works on different principles, has different advantages and disadvantages. We will briefly look at each one of these type of crystallizer. Okay, this is called a forced circulation crystallizer. So what happens? You have a crystallizer, there is a heat exchanger. Okay, so he heats up. Okay, so the vapors are formed, vapors go up, so the solution becomes supersaturated. So when the solution becomes supersaturated, crystallization takes place. So we are feeding in here, we are taking out the slurry. So the feed that comes in gets heated up, so vapors are formed, vapors are removed. When the vapors are removed, the solution becomes supersaturated, so the crystals are formed or existing crystal starts growing, slurry is out here. So there is a recirculation loop. This happens automatically. Why? As the vapors are formed, the density goes up, the liquid has a higher density, so there is an automatic circulation that is taking place. So the circulation is happening externally, there is a heat exchanger located here. So here the liquid and the vapor are separated, so the vapor comes out. If it is water, it will be water vapor, if it is a solvent, it will be a solvent which we can collect it. This is called a forced circulation crystallizer. There are no agitators in this type of design. So they are also called mixed suspension, mixed product removal. As you can see, it is suspended, you are removing product combination. We can have single or multiple effects. Okay, I will talk about what is a single effect and a multiple effect later. It can have different types of recompression, that means the vapor can be recompressed using thermal or mechanical approach. So they operate at low vacuum to atmospheric pressure. If you want to remove the vapor, if it is a solvent, we utilize vacuum so that the solvent gets evaporated very fast. If it is water, we need to heat it up considerably, and then we need to apply vacuum as well so that the water vapor gets removed. Sometimes crystals you do not want to heat up too much because the crystal, the color texture of the crystal gets disturbed if you are resorting to very high temperature. So we can use this for sodium chloride, food grade or technical grade, potassium nitrate, sodium sulfate, potassium sulfate, ammonium chloride, citric acid. So a lot of products could be crystallized by this. It is a very simple system, and we can scale it up to very large scales, and it is a typical industrial type crystallizer. Let us look at another one. This is called Oslo type crystallizer. So what is happening here? So here we are introducing a superheated solution, and the vapor goes up because maybe you are applying a vacuum. So when you do that, the solution gets supersaturated, so it starts coming down. So there is a crystal bed here and the solution flows through. When the solution flows through the crystal bed, the crystals become bigger and bigger. Okay, so bigger and bigger crystals are settling here, and then the solution again rises, which goes to a external pump as well as a heating system. So you are heating up your solution, which enters here, vapor is removed or flashed because you may be applying a vacuum here. So the supersaturated solution comes down and there is a bed of solids. As the supersaturated solution comes in contact with the bed, the size of the crystals grow, so the supersaturation goes down, and now again it is sent to recirculation, reheating and so on actually. Okay. So this is how this system works. So in this system you are building up the size of the crystals because there is a bed of crystals and your supersaturated solution flows through the bed of crystals. So this is again an industrial type of operation, it is a huge setup. So it is called a classified suspension crystallizer, it is very old design. So your desupersaturation of the mother liquor happens because the supersaturated solution comes in contact with the crystals, and you are keeping most of the crystals in suspension without contact by a stirring device, thus enabling production of large size crystals. So the crystals that are at the bottom of the bed are going to become larger and larger because they come in contact with the supersaturated solution. So again this is used for ammonium sulphate, sodium sulphate, silver nitrate, monosodium glutamate, monoammonium phosphate, large number of products can be done with this. We can get very large crystals with this type of arrangement. Then you have the draft tube baffle crystallizer. So you will have the draft tube here, there is a circulation. So what happens in a draft tube? The solution rises because of the presence of vapor. As soon as the vapor gets disengaged and starts moving up, the liquid is heavy, so it starts coming down. So the solution rises because of buoyancy force, and as soon as the vapor gets disengaged, the liquid is heavier, so they start coming down. So there is an automatic circulation created here. Okay. You are also agitating so that you are not allowing the solids to settle down, and you are introducing a superheated solution here. So as the vapor gets disengaged, they become supersaturated. Okay. At the same time you also have the recirculation pump here. Okay. So this particular portion contains solid and the liquid going round and round because of the circulation created by the draft tube. So this can be operated at vacuum here, you may be applying a vacuum here, you are having a recirculation pump here so that the liquid is moved round and round into the vessel. Now the slurry can be withdrawn from the bottom here, where because you are going to keep accumulating your crystals here, and then later on you can resort to either centrifugal operation or you can resort to filtration so that the solid is separated from the liquid. This is called a draft tube baffle crystallizer because it has got a draft tube, and the draft tube gives you the natural recirculation that is possible. In the center there is buoyancy, so the liquid and the solid and the vapor rises, and on the sides the liquid and the solid comes down because of the weight. Another one is called the induced circulation crystallizer. So we are trying to induce the circulation in this particular crystallizer. Okay. Again the slurry is withdrawn from there and you are inducing this type of circulation at the bottom. So we are introducing a superheated solution from heater and a recirculation pump from the bottom actually. Okay. So here on the top you are going to get a clear mother liquor overflow, and then at the side you are going to also have a induced circulation taking place here. Okay. And the vapor is removed from the top. So what is the advantage of this? It is almost like a draft tube baffle crystallizer. So in a draft tube you have a draft tube crystallizer which creates the circulation, and there is no internal agitation in a draft tube, whereas in an induced you also add an agitation so that you do not allow the solids to settle down. So we can use it for a large number of applications. It also works like this mixed suspension, mixed product removal, that is the original one, and we can get very narrow crystal size distribution with this because you are not allowing the crystals to settle down. Okay. So that is the advantage of this type of induced draft circulation system. So it has been successfully again used for large number of products starting from ammonium chloride, sodium chloride, ammonium chlorate and so on actually. So how do you select the solvent? As I said, solvent could be water or it could be an organic liquid. So selection of the solvent is very, very important. Okay. If you have a non-polar solid, it will dissolve nicely in a non-polar solvent, and a polar compound will dissolve nicely in a polar solvent. So you need to think about what type of crystals you want to prepare. It should dissolve the entire compound at the boiling point of the solvent. Okay, that is very, very important. So it should not be partially dissolving the solid, it should be able to dissolve the entire compound. At room temperature it should not dissolve any of the compound. That means the solid at high boiling point should be completely in solution, but when we bring it down to room temperature the solid should completely come out as a crystal or a precipitate, and the solubility of the solid at room temperature should be practically 0. Otherwise at room temperature if some solid is present, then that is going to go as a waste, we will not be able to recover that particular amount. And the solubility of the solid or solute should be very different from the solubility of the impurities. If the impurity solubility is high, then you are in trouble, you will not be able to remove the impurity from the solid. So the solubility of the impurity should be low, and the boiling point of the solvent should be much below the melting point of your compound. Otherwise what happens, if the boiling point is very high, then your crystal will start melting. If it starts melting, then it will be very difficult for you to separate out, and if the solids melt it will form tarry product, it will not be accepted by the customer. So it should also have a low boiling point. We do not want the boiling point to be very high, then what happens, you may have to resort to high energy expenditure. It should not react with the compound, that is also very important. Otherwise if it starts reacting, then you will not be able to do the crystallization process. It should be non-flammable, that is very important, that is from the safety point of view. It should be not toxic, because when it is in an industrial scale it should not affect the operators, and it should be cheap. We do not want an exotic very expensive solvent, and every solvent liter we lose, we are losing money. So what are the commonly used solvent? Water, because it is the most non-flammable, non-toxic, cheap and so on, but only problem is it has got a very high boiling point. So we have to raise the temperature, we have to resort to vacuum and so on, so the removal cost is very high. Acetic acid, it is useful, it will but it will react with alcohols and amines, and it has got a very high boiling point. Dimethyl sulfoxide, DMSO, it is not used in crystallization, it is used in reactions. Methanol will dissolve compounds of high polarity. Acetone, that is very good, but problem is it has got a very low boiling point. So if you are operating this type of crystallizer in a hot country or in tropical place, some acetone is lost. 2-butanone or MEK, methyl ethyl ketone, that is very good, it is a very good solvent, boiling point is much low, 80 degrees, and it is not as bad as acetone. Ethyl acetate, again it is very good. Dichloromethane, it is good as a solvent pair, but it has got very low boiling point, so it is absolutely no as a single solvent. Diethyl ether, again it is good as a solvent pair with some other solvent, but very bad boiling point. Methyl tertiary butyl ether, not bad, 52 degrees, so it can be used in colder climates. Cheap. Dioxane, easy to remove from crystals, it is slightly carcinogenic, but the boiling point is high. Toluene, it is a very good solvent for crystallization, but boiling point is very high. Pentane is good for non-polar compounds because it is an organic, so it is very good. So but it can be used in combination with some other solvent, not per se because low boiling. Hexane, it is very good, 69 degrees centigrade, it is good for hydrophobic chemicals, phytochemicals and so on. It can be used as a solvent pair, that means it can be used in combination with another solvent. Cyclohexane, it is cheap, similar to hexane, 81 degrees, very good for hydrophobic compounds. Petroleum ether, cheap, it has a range of boiling point 30 to 60, it can be combined with pentane and so on. Ligroin, it is a mixture of saturated hydrocarbons with properties similar to hexanes actually, you know. So it has got a range of boiling point rather than single value. So many solvents, low boilers, high boilers, hydrophobic, hydrophilic, so you need to select depending upon your ambient conditions, the type of solids you want to precipitate or crystallize out and so on actually. So if no single solvent is satisfactory, we can have combinations of two solvents, okay, that is called a solvent pair, but they should be miscible with each other, they should not be separating out, then we are in big problem. So we can have acetic acid water, ethanol water, acetone water, dioxane water, so nice polar solvent. Or we can also have ligroin, which is almost like hexane type, dichloromethane, ligroin, ethyl acetate, cyclohexane. So a large number of solvent pair is also available which can act as a good solvent for crystallization if you think a single solvent is not very satisfactory. Peptides can be crystallized, as you know peptides are short amino acid chains and they do not have any conformation like protein, so they are quite stable, they do not lose their structure and properties in right conditions. So generally how do you crystallize this? By evaporation. So we raise the temperature, so the solvent evaporates. Some peptides adopt stable conformation, metal ions or cations, so that is like a cyclic peptides like antibiotics and so on actually, okay. So optimal size for peptide crystals are 0.2 to 1 mm. So how do you do peptide crystallization? We can decrease the solubility by adding an anti-solvent, that means a liquid that if added to a solution reduces the solubility, okay, like crystallization of K potassium nitrate from his aqueous solution through salting out by isopropyl alcohol. So when I add isopropyl alcohol, the solubility of potassium nitrate decreases in aqueous solution, or increasing concentration by a chemical reaction, okay. So there is a chemical reaction, so the concentration increases, so it comes out as a precipitate. So like in precipitation of calcium sulfide from sulfur dioxide and lime. So these are the two ways by which we can precipitate or crystallize peptides. There are many problems that are encountered during crystallization, so they can be related as problems because of crystals or particle related, or problems because of the equipment or the crystallizer related. So particle related could be because of presence of impurities, solvents, reactions, boiling points, miscibilities, viscosities and so on. Crystallizers is more related to equipment, mixing, agitation, heating, flow rates, vapor removal and so on actually. So the crystal related problem leads to low crystal yield, poor solid liquid separation, poor drying and fluidization, that means after your crystallization you are not able to dry fully, or poor end use properties, that means the final product is not having all the properties of the real solid because of some impurities or because of removal of solvent or because of the type of crystal that is formed and so on. So there are different types of crystallizers, the mode of crystallization. We talked about types of crystallizers, now we look at mode of crystallization. So we can have a feed solution, we can have a vertical tube evaporator, so you form a liquid and a vapor. So when they enter the crystallizer, the vapor evaporates and goes up, so you get a supersaturated solution, so the crystal slurry forms. Now this vapor goes in, okay, and which is removed by vacuum, that is called the evaporator cum crystallizer. So you are evaporating the solution and then you are crystallizing because you have formed the supersaturation here. The multi-stage crystallizer is a very energy integrated system. So what happens here is we are heating it up, so there are vapors that are formed, so crystals are formed, so which is removed in a filter, and this solution goes into the next crystallizer where again you are heating it up, and again some more crystals are formed, and the remaining solution goes to the third crystallizer, and so on. So we have very pure crystals formed in the first stage, later on you may be having impure crystals. So you are trying to remove as much of the solid that is possible by having several stages. So the idea is that you do not leave any solid in the mother liquor, that is called the multi-stage crystallizer. But then you need to have several vessels and several filters, and each vessel is heated up so that supersaturation is achieved. Another type of crystal, that is called the multi-effect crystallizer. That means the vapor that is generated, which is very hot in one stage, is used to heat up the second stage. That means you do not use any fresh steam in the second stage. So you use steam in the first stage to heat the solution, vapor is formed, so the solution becomes supersaturated, crystals are formed as crystal slurry. Now this vapor, which is very hot, goes to the second stage as the heating fluid, which heats the solution that is present and supersaturated, leading to crystals. Now this vapor, which is formed in the second stage, goes to the third stage to heat up the solution present. So the vapor in the first stage goes to the heater in the second stage, and the vapor in the second stage that is formed goes to the heater in the third stage. That way you are using steam only in one stage. That way you are economizing on the steam necessary to produce these crystals. This is called the multiple effect crystallizer. In fact, this type of designs are used in manufacture of sugar crystals. So you may have 3 or 4 different stages or effects of crystallizers, where you get crystals in each one of these stages, and the amount of heat used is extremely low. So by applying vacuum in the very final stage, you are drawing the vapor from the stage 1 to stage 2 to stage 3 to stage 4. So the amount of heat required or the amount of external heat you are supplying is minimal here only. You are not supplying heat in each one of these stages. Okay. So what is the rate of heat required to evaporate a solvent? This is just the heat balance. If you assume that there are no losses, the rate of heat required, you are going to evaporate the solvent, right. So you are going to have the lambda, that is the heat of vaporization of the solvent, into m bar. M bar is the rate of evaporation of the solvent. So the rate of heat required on the left hand side is equal to the rate of evaporation of the solvent into lambda, which is the heat of vaporization of the solvent. Okay. So if the heat of vaporization or the latent heat of vaporization of the solvent is high, the amount of heat required is also very high. That is why in the previous slides when we talked about locating a solvent, we said that it should have lower boiling point or lower heat of vaporization, so that the amount of heat required is also very low. So the crystals of various sizes are formed which grow in time, and generally although you would like to have a monodisperse, that means crystals of one single size, it is not going to be, it will be following a Gaussian or a uniform distribution. So that means some crystals will be older, so they will have larger size, some crystals will be young, so they will have smaller size. So the dominant crystal size dc is given by 3g into tau. Tau is the residence time in the vessel, that is volume in the vessel divided by flow rate or feed rate, and g is the crystal growth rate. So fraction of crystals in this size range will be 1 minus e, that is exponent raised to the power minus dc by g tau. Okay, that is the equation. So the fraction of the crystals in this size range will be like this actually, and the crystal growth rate I talked about based on the G is equal to delta L by delta T, which is constant. That means change in the dimension, unit dimension of the crystal as a function per time is a constant. So to conclude, we can say crystallization is the most important downstream process, which is generally resorted to at the very last stage, where you are interested in a solid product after you have done a recovery, after you have done purification of your product. So we can resort to crystallization of peptides, cyclic peptides, metabolites, salts and so on, and the main goal is to remove the impurities that is present, drying to remove any solvent or water that is present, thereby the product will have longer shelf life or stability. Sometimes your customer would like to have the product in a solid form because he would like to formulate your product in either in a biopharmaceutical product or in a cosmetic type of industry. So again you need to have your product in a crystal form. And I also mentioned that there are 7 different classes of crystals, moving from cubic to orthoclinic, orthorhombic and so on, and all solid crystals will fall into this group. So by putting them into different groups, we are able to generalize on the characteristic of each group.